Welcome. In this video, I'm going to go over solutions for the Paper 3 exam that was given in SL Chemistry in May of 2016. So Part A looks a little different. The whole Paper 3 looks a little different because there's Part A, and this has got some experimental questions here, and it says the absorption of infrared or IR radiation by molecules in the atmosphere affects global temperatures. And they want to know, using the graph, giving your reasons, are oxygen and ozone greenhouse gases? So I see oxygen's absorption band right here, and it's clearly within the UV area, whereas O3's is just as clearly in the IR area. And it says at the top, absorption of infrared by molecules in the atmosphere affects global temperatures. So O2 absorbs in UV range, so not a greenhouse gas. I'm just going to put GG for greenhouse gas. O3 absorbs in IR range, so it is a greenhouse gas. And it really was that easy for the first one. Part B is broken into several questions, and you got a bunch of data here, different molecules, and then something called the integrated IR intensity, the molecular dipole moment, and the GWP over 100 years. And they talk about the integrated IR intensity, the measure of the extent to which it absorbs infrared, and then the global warming potential is the contribution over the 100-year time that it specifies. So use the integrated IR intensity data in the table to estimate the value for CF4. Well, when the first chlorine drops off right here, that was an increase in intensity of 260. When the second one came off, the increase was only 165. And when the third one came off, the intensity was back to 230. So not a real clear pattern here. It's definitely increasing. If you're going to predict this would drop back to 150, seeing the, every other pattern here, wondering if it has to do with, the balance and stuff, I think that would be legitimate to predict around 1350. I also think it would be just as legitimate to predict it to be closer to the 250 range or up around 1450. And then 2 says, explain the increase in molecular dipole moment as one chlorine atom is replaced with fluorine to produce Cl3F. And in fact, we see a slight increase when the second fluorine comes on and then a slight decrease with the third one. And what's happening is I have a tetrahedral molecule that originally had 4 chlorines on it. And with 4 chlorines, even though there's polar bonds, the tetrahedral symmetrical arrangement allows for the negative charge to be surrounding the positive carbon. And so there's no net dipole. But when I put the fluorine on here, now the fluorine is going to pull more strongly than the chlorines can, and the more electronegative fluorine creates a dipole in spite of the tetrahedral shape. So by having 1 fluorine and 3 chlorines, there's no longer the balance there had been. Part 3, outline the relationship between GWP over 100 years and integrated IR intensity for CCl4 and then CCl3F, CCl2F2, and CClF3. And what you'll notice is that it's a direct relationship, not linear, but direct. As one increases, the other increases. Examine whether there is a general relationship between integrated IR intensity and molecular dipole moment. If you look at the first 2, you have CO2 and CCl4 both at 0. Yet CCl4 has a much greater intensity. Number 4, CCl2F2 and CClF3 were developed for use as refrigerants, but are now being replaced by other chemicals. Comment on their use with reference to values in the table and other environmental concerns. Well, they have high absorption of IR, and a long GWP. So not only do they absorb it, but they hang around a long time. So they will have a negative impact on the environment for a long time. Number 2, a student wished to determine the concentration of a solution of sodium hydroxide by titrating it against a 0.1 molar aqueous solution of hydrochloric acid. 4 grams of sodium hydroxide pellets were used to make a 1 molar or 1 liter aqueous solution. 20 cc samples of sodium hydroxide solution were titrated using bromothymol blue as the indicator. So outline giving your reasons how you would carefully prepare the 1 liter aqueous solution from the 4 grams of sodium hydroxide pellets. So what I would do is I would dissolve the pellets in about half my water, so in approximately 500 milliliters of distilled water, in a volumetric flask, and then fill to the 1 liter mark. Because you want to be sure all the pellets have dissolved, and you want to be sure to account any volume that the pellets may occupy into your 1 liter total solution. B1, state the color change of the indicator that the student would see during his titration using section 22 of the data booklet. And what you need to realize is bromothymol blue is blue in base, and it becomes yellow-greenish in an acid. So you have to take a look here. You're starting with 20 cc's of sodium hydroxide, and you're adding the acid to it. So the color change you're going to see is from blue to that green-yellow color. The student added the acid too quickly. Outline giving your reason how this could have affected the calculated concentration. Well, if he overshot, if the endpoint is overshot, then your moles of acid and moles of base are inflated because you take a greater volume times molarity to determine those moles and use the moles of acid with the molar ratio to determine the moles of base, are increased, and this would then therefore increase the concentration that you calculate for the NaOH. And part C suggests why, despite preparing the solution and performing the titrations very carefully, widely different results were obtained. And the most likely reason is trouble knowing when the endpoint has been reached. And that's due to detecting the color change by sight. So anytime humans have to make the judgment, it's going to introduce some air. Then, as far as the options, we looked at option D, or spent some time on medicinal chemistry. So those are the questions I'm going to go through. Starting with number 16, penicillin was one of the first antibiotics to be isolated and identified for its ability, blah, blah, blah. Explain the importance of the beta-lactam ring. And the beta-lactam ring is highly unstable or highly reactive, whichever way you want to think of it. So it will break open and bond with an enzyme. And specifically, it'll bond with the transpeptidase enzyme. And if you can't remember the name, just realize it's going to bind with the enzyme that helps bacteria form cell walls. And when that happens, bacteria cells are going to rupture without the wall to contain them. And when they rupture, they die. Two dangers of the overuse of antibiotics. The big thing is the development of drug-resistant bacteria, development of drug-resistant bacteria. Which can be incredibly dangerous, because if you end up with an infection, a bacterial infection that no bacteria or no antibiotic can touch, it could definitely be life-threatening. But other problems is if you overuse antibiotics, you can develop some GI problems. In fact, some people have developed diarrhea so severely it's been fatal. But you can have a variety of GI problems, such as the probiotic balance being upset. Women often develop yeast infections as a result of it. Another concern is it drives up costs as new antibiotics need to be developed. Because every time we have bacteria that don't respond to our current antibiotics, we need to look for another antibiotic to kind of keep outsmarting the bacteria and their mutations. Number 17, opiates have been used for thousands of years to alleviate pain. The structure is found in section 37. Diamorphine or heroin can be synthesized from morphine. Identify the reagent necessary for this. So if you look, what's happening is the 2OH groups on morphine are becoming a COOH group on the heroin. So what you should recognize is you have an alcohol converting to, actually that's not a COOH group, it's a COO group. So you're forming an ester. So the reagent is you need an acid, so ethanoic acid is often used. And then the byproduct is the COOH and the OH are going to get together, and it's a condensation reaction because H2O is a byproduct. Part B, the reaction can be monitored by infrared spectroscopy, so identify two ranges that would help distinguish the two compounds. Well, the big thing in morphine is there's an OH group that's part of an alcohol. So the IR spectrum that corresponds to that is there would be a peak at 32 to 3600. For this hydroxyl, sorry about that, for the hydroxyl group. Again, in the alcohol, because there's another OH peak, but that's for something in a carboxylic acid. And then in the dimorphine, there would be a peak at 1700 to 1750 for the oxygen double bonded to carbon in the ester group. Part C, discuss how the differences in structure between morphine and diamorphine affect their absorption in the body. Diamorphine, or heroin, becomes less polar without the two hydrogen bonds that are found in the OH on morphine, so it's absorbed much better. It's absorbed more completely and more quickly, making it a far more dangerous drug. More completely and quickly. Number 18, magnesium hydroxide is the active ingredient in a common antacid. Formulate the equation for the neutralization of stomach acid with magnesium hydroxide. So I've got MgOH2. Stomach acid is just a dilute HCl. So I'm going to end up with H2O and MgCl2. So to balance this, I will need a 2 here and a 2 here. And so determine the mass of HCl in grams that can be neutralized by the standard adult dose of 1 gram of magnesium hydroxide. So 1 gram of magnesium hydroxide, if I change that to moles, it's got a molar mass of 58.33. So we're talking 0.0171 moles of magnesium hydroxide. And I can see it's a 2-to-1 ratio with HCl. So we're really talking 0.0343 moles of HCl, which has a molar mass of 36.46 grams per mole. So I could expect to neutralize 1.25 grams of HCl. Part C says compare and contrast the use of Prilosec and magnesium hydroxide. Well, Prilosec is what's known as a proton pump inhibitor. And the idea with proton pump inhibitors is it doesn't allow the stomach lining to pump or release the acid. So if the acid doesn't reach the stomach, it's not an issue. But antacids like magnesium hydroxide deal with acid already in the stomach. So oftentimes things like Prilosec, the proton pump inhibitors, have to be taken before the food to get a head start on it. But if you've already eaten and you've had the acid release, then an antacid is going to be more effective. And number 19, radioactive isotopes are used in a variety of medical procedures, including medical imaging. Identify 2 types. So they didn't say 2 examples of medical radioactive waste, but 2 types. So I assume they're talking about low-level waste and high-level waste. And low-level waste needs interim or short-term storage in a sealed container. And then after hours or days, depending upon how low level it is, then it can be transferred to a landfill or some other disposal. But high level waste usually are in cooling ponds, and that can be for quite a long time, like years, and then are transferred to heavily shielded containers. And if you can find a place where you can bury it in the earth, where it's geologically stable, and whoever owns that area is willing to let it happen. Otherwise, many of these containers are just sitting around waiting for a place to be permanently deposited. So an ethical implication of using nuclear treatments is the amount of high-level waste, especially, the amount of high-level waste generated does not have a good disposal plan. We keep accumulating more and more of this waste, and we're really not sure what to do with it, but we're not sure what to do without it. And so without a good disposal plan, it poses both environmental and health risks for those around it, wherever it is stored at.